In pursuit of transferring technical knowledge and just to gear up the new engineering entrant, myself Pranav is here to deliver today's presentation, Power Transformer Part 18. As the topic is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with basic properties, advantages and disadvantages of amorphous metallic alloys. Let's discuss with the properties of amorphous metallic alloys. Amorphous metal alloys is the key composition of iron, boron, silicon alloy having with a non-crystalline structure produced by ultra-rapid quenching of molten alloy with the cooling rate of 10 to the power 5 to 10 to the power 6 Kelvin per second, where 0 Kelvin equals to 273.15 degrees centigrade. Number 2, have excellent soft magnetic properties with better surface quality. Have high yield strength, that is more than 1300 megapascal or 132.563 kGa per millimeter square, combined with an elastic elongation of more than 1.5%. Number 4, have a very high level of hardness and therefore little abrasion, which is particularly important for making heavily stressed components. Number 5, have high permeability. Number 6, comparatively high electrical resistivity or low electrical conductivity. Number 7, electrical resistance is being almost temperature independent. Number 8, low magnetic loss. Number 9, exhibits a higher corrosion resistance. Number 10, lower coercive force. Lower coercive force, which is almost 1/3 of CRGO steel, that is cold rolled grain oriented steel. A very desirable feature of low conductivity and low coercivity is rather counterbalanced by the lower saturation magnetization, which is almost at 1.56 Tesla, whereas for CRGO steel that saturates almost at 1.9 Tesla or more. Number 12, brittleness properties as compared to CRGO steel is much higher. Number 13, stacking factor is one of the most important design parameters of transformer core manufacturing process, as because a stacking factor of less than 1 has indicated to reduce the flux carrying capacity of the iron core accordingly. Stacking factor is defined by the ratio of effective cross-sectional area of the transformer core to the physical cross-sectional area of the transformer core, that is ferromagnetic material plus insulation. So it is obvious that the stacking factor is directly related with the core lamination thickness. Higher the lamination thickness, higher will be the stacking factor, that is approaches to unity. As a matter of fact, core consisting of stacked thin laminated sheets always have the stacking factor less than unity, where as stacking factor of unity implies no laminate at all. Stacking factor is of 0.9 to 0.95 for the CRGO core transformer and 0.8 to 0.9 for the amorphous core transformer. Now, advantages compared with CRGO core transformer. Amorphous metal alloy is the key composition of iron, boron, silicon alloy, that is iron Fe 78%, boron B 13%, silicon 9%. Number two, it offers maximum saturation flux density of almost at 1.56 Tesla. Metal alloy is easy to magnetize, and that has been reflected by the relationship between the magnetic induction B and the applied magnetic field H. Narrowness of the BH loop, the high permeability of low hysteresis component of magnetic losses would have to indicate the relative ease of magnetization. Number 5, eddy current component of magnetic losses is also to be minimized. Number 6, compared with CRGO steel core, amorphous metal transformers have the superior harmonic wave tolerance. Number 7, if the lamination thickness is very thin, then this can have a major influence on the machine performance. Total electrical resistance, number 8, would have been higher as because available amorphous metal ribbon thickness is of the order 0.025 millimeter, which is rather 10 times thinner compared to CRGO steel lamination. Number 9, magnetic component of having higher electrical resistance, almost 2 times higher than that of CRGO steel lamination, may have to surpass or may have to suppress rather the flow of eddy current, causing to minimize eddy current component of magnetic losses. Again, I repeat, number 9, magnetic component of having higher electrical resistance, almost 2 times higher than that of CRGO steel lamination, may have to suppress the flow of eddy current, causing to minimize eddy current component of magnetic losses. Number 10, as due to smaller temperature rise within the coil, that indicates higher be the relative efficiency of amorphous metal alloy core transformer. Number 11, in case of amorphous core transformer, as the reluctance offered by magnetic path is about 1/4 of reluctance offered in conventional CRGO core transformer. So the magnetic asymmetry would have to be reduced, resulting a reduction in zero sequence current. Number 12, specific core loss for CRGO core transformer is typically at the order of 0.9 to 1.5 watt per kg, whereas for the amorphous core, this loss will be around 0.1 to 0.2 watt per kg at 50 hertz and saturation flux density of almost at 1.4 to 1.5 Tesla. Amorphous metal transformer has go rather has to operate with reduced core loss almost by 70% and magnetizing current as low as 55 to 60%. And overall temperature rise is much less as compared to conventional CRGO steel core transformer of same kVA rating. Again, I repeat, number 13, amorphous metal transformer core has to operate with reduced core loss almost by 70% and magnetizing current as low as 55 to 60%, and overall temperature rise is much less as compared to conventional CRGO steel core transformer of same kVA rating. Thus, such type of core exhibits an excellent overload tolerance. Notable features. Amorphous metal alloys have shown a better option for the formation core structure as compared to the efficiency of transformers made from conventional CRGO steel core. Because of excellent electromagnetic and mechanical properties, one, exceptional hardness and the combination of high yield strength and low stiffness would have imposed to formulate the metallic alloys of achieving very high ability to store elastic strains energy as well as to release it. Due to lack of crystalline, number two, due to lack of crystalline structure, the metal alloys have very good corrosion resistance. Number three, resulting of low coercivity and high permeability, they have excellent soft magnetism with easier magnetization process. As of low coercivity, high permeability, high resistivity, and faster flux reversal, so there would have been a lower magnetic loss. Disadvantages. The cutting and forming of amorphous metal laminations is quite expensive as because of significant wear out of tools due to its hardness of the metallic alloys over C80 Rockwell. And as the metal ribbon thickness is of the order of 0.025 millimeter, so a greater number of stamping operations are being handled as well. Due to complicacy of in manufacturing technique, the overall cost of amorphous core transformer is approximately 20 to 30% higher than that of the conventional CRGO core transformer. Amorphous core transformers have some obvious advantages over the conventional CRGO transformer, but after years of service, these advantages are thereby eroded due to limitations of the material characteristics. Most important. One, decline in efficiency over time. Amorphous metal has the limitations due to its brittleness property and does not have the strength to withstand continuous mechanical stress. Stress and strain as developed within the core due to have certain unwarranted vibrations, step loads, and the short circuits, then there would have been a cause of degradation of the physical characteristics of amorphous metal ribbon and ultimately leads to a higher no load loss over time. Two main constituents are responsible for transformer vibrations. A winding vibration would have been the effect of electromagnetic force as generated by the interaction of the current in a winding with leakage flux. And B, iron core vibration is mainly caused by the magnetorestriction forces in the core laminations. Number 2, intent for major failure. Because of brittleness property of amorphous metal, so during the process of manufacturing, if any small broken fragment is somehow present at the core segment, then this can cause partial discharge, which may lead to have degradation of the oil over time and intents for major breakdown. The repairing job is much more cost and labor intensive as amorphous transformer cores are very brittle and fragile. Thickness is of the order 0.025 millimeter. Repair at site is rather impossible as because it requires extreme care during core assembly and disassembly and assembly, and also for which specialized lines of equipment should have to be needed. Again, I repeat, repair at site is rather impossible as because it requires extreme care during core disassembly and assembly, and also for which specialized lines of equipment should have to be needed. So, repairing job is often to be practicable only for large transformers. Poor withstanding ability to counter stress of short circuit fault. As the material fragility is the most problematic constraint, so in transformers with core material amorphous metal alloy ribbon has the limitation only to form square or rectangular cross section of the core. Rectangular section design of the core has also to make the windings of rectangular construction, but the distribution of forces on a rectangular shaped core would have always been uneven. The resultant effect is to have a lower ability to withstand the stress of short circuit fault along with all sorts of associated constants. See figure 84. Transformer core showing HV and LV windings with associated forces. See the direction. Core, HV winding, LV winding, direction of forces on HV winding and LV winding, deformed of LV winding due to short circuit. Poor overload capacity. As the saturated flux of amorphous metal is much lower than that of the CRGO steel, so amorphous core is easy to be overexcited. Thus, overload withstanding capacity of amorphous core transformer is much lower than that of the conventional CRGO steel core transformer. Sometimes 80% of load might have been exhibited some sort of erratic phenomena in case of amorphous core transformer, whereas Sergio steel core transformer can run with 120% of load for a certain period. This will be the advantage of Sergio steel over amorphous alloy steel's core. Higher noise level. In amorphous core transformers, core is made of very thin ribbon of thickness 0.025 millimeter and obviously cannot withstand any sort of compression during core manufacturing process. Hence, there would have been some larger gaps in between each layer of the thin ribbon sheet. These gaps have therefore to contribute humming noise emitted through the material magnetorestriction effect, while AC currents produce a changing magnetic field. Having of the same capacity, noise level in amorphous metal transformers are significantly higher because of the larger volume of core material compared to conventional Sergio transformers. Increase in weight and volume. Maximum saturation flux density of amorphous metal alloy is almost at 1.56 Tesla, whereas for Sergio steel that saturates almost at 1.9 Tesla or more. So, in order to achieve the same capacity of the conventional Sergio steel core transformer, an amorphous transformer will require a larger core, increasing the size of the transformer and its volume, which also must be accompanied with exorbitant cost involvement. This has also resulted to have a larger installation areas with requisite support structures. Therefore, amorphous alloy is more suitable for miniature size of transformers and distribution transformers, which are usually designed for lower flux densities. 7. Unavoidably produced sheet splinters. In amorphous core material, as the core is made of very thin ribbons of thickness 0.025 millimeter, so sheet splinters are produced during the core manufacturing process. These splinters, which are very light and smooth, would always have the tendency to adhere and stick together easily at the core overlapping area. It is virtually impossible to remove these core splinters, which would therefore contaminate the dielectric fluid, that is oil, transformer oil. With the flow of fluid, there is possibility to ingress into the actual windings, which may have to instigate ultimate failure of the windings. Leakage flux paths which pass through the cross section of the conductor would therefore have to induce voltages, which also vary over the cross section. These induced voltages would create circulating currents within the conductor, causing additional losses. These losses are termed as eddy current losses in conductors and are thereby varying as the square of the frequency. The conductors used in power transformers are typically stranded with a rectangular cross section. Individual strands may be subjected to differences in flux field due to their respective positions within the winding, which create differences in voltages between the strands and drive circulating currents through the conductor loops. However, proper transposition of the strands cancels out difference of voltages and has to eliminate or greatly reduce the circulating currents, which helps to reduce eddy current losses at the end of the winding. Number two, load loss on performance parameters. There are two components that constitute transformer load loss. A, loss in the current carrying parts, which is a function of the resistance of the winding materials and varies with the load on the transformer, that is I square R loss. Number two, that is B, stray loss, which is due to eddy currents induced in other structural parts of the transformer, that is in the tank structure. However, while designing a power transformer, the concept of life cycle cost is considered to be very much relevant rather than to make it establish as the most efficient energy transfer equipment. Resistive losses as due to eddy current losses in conductors represent the main component of the load dependent or the variable losses and are designated as I square R of copper losses. As influenced by the winding currents, conductors in transformer windings are subjected to have alternating leakage fluxes. Again, I repeat, as influenced by the winding currents, conductors in transformer windings are subjected to have alternating leakage fluxes. Continuously transposed conductors, that is CTCs, are basically constituted with thin layers of insulation, which helps to reduce the space demand for the windings, and the heat as generated is evenly distributed across the winding. Hence, emanating of leakage fluxes from the current carrying windings are mainly responsible for producing stray losses, and structures adjacent to the winding will tend to be affected easier by these leakage fluxes. Stray losses would have to depend on the amount and intensity of leakage flux, permeability, as well as the resistivity of the metal structures and distance between metal structures and the source of leakage flux. Though the stray loss relatives to all losses may not necessarily be large, but can lead to dangerous local overheating in the metal structural parts like flitch plates, end frames, tank walls, etc., which may become an issue in the operation of transformers. In order to minimize load losses, which are categorized as one, resistive losses, that is I square R losses. Number two, eddy current losses in windings as due to alternating leakage fluxes cutting the windings. Number three, stray losses in conductor leads, core framework, and tank as caused by the action of load dependent stray alternating fluxes. designers used to interact for restricting load losses. Design with the lowest resistivity winding material, that is higher conductivity copper material, is mostly preferable. Designed with lowest possible number of winding turns. However, this indicates that the core material as provided must be of higher magnetic flux density, that is offers maximum saturation flux density, also to have provision of largest practicable core cross-sectional area, which in turn causes more iron loss. Designed with increasing the cross-sectional area of the HV winding and LV coil conductors, which obviously has to instigate an increase in winding eddy current loss so as to generate higher leakage flux, cutting the winding conductors. This has also resulted for poorer winding space factor. Best possible solution is to use transposed conductors, that is CTC conductors, Stray losses in transformer can be reduced significantly by applying certain indicative design mechanism. Eddy current is the main component of stray losses. Continuous transposed conductors has to be used depending upon the current and sizes. Two types of shields are generally used to restrict stray losses due to leakage of magnetic flux. A, yoke shunt, and B, tank shield. With yoke shunt and tank wall shield, it is necessary to provide suitable earthing arrangement. Design of magnetic shielding from HV side would protect the tank wall best while keeping stray losses to a minimum. See the diagram. Effect of eddy current shielding and be influenced by two kinds of elements, that is magnetic resistance for non-conductive areas. Another is magnetic impedances for conductive parts. See the diagram. HV side top shunts, laminated core, LV side top shunts, LV side bottom shunts, end shield, end side shunts, core clamps, yoke beams, HV side bottom shunts. Now see the point. It has been evaluated that the gap between horizontal shunt and yoke must be kept reasonably small for effective control of leakage flux. Again, I repeat, the gap between the horizontal shunt and yoke must be kept reasonably small for effective control of leakage flux. Short circuit impedance. Winding arrangement has an immense effect on short circuit impedance, which is a major parameter of the transformer design, manufacture, and operation. Value of the short circuit impedance must have to affect the electromagnetic force of the transformer and the voltage fluctuation of the power grid. Short circuit test helps to determine the value of short circuit voltage, which is one of the most basic transformer characteristics. The short circuit voltage VSH of a transformer is usually expressed as a percentage of the rated primary voltage, that is V1. That is VSH percentage equals to VSH by V1 into 100. The short circuit impedance is therefore be determined on the percentage of the rated voltage to be supplied as the primary coil, that is HV side of the transformer, when the secondary coil LV side is shorted for having rated current in the primary coil. This short circuit impedance has also to represent the impedance of the transformer. The higher the impedance voltage, the higher will be the regulation. Again, I repeat, the higher the impedance voltage, higher will be the regulation. Hence, short circuit impedance is not only an effective parameter to limit the short circuit currents, but also responsible to determine the regulation, that is, voltage drop across the transformer under load conditions. It can be expressed in percentage of rated impedance equal to percentage value of short circuit voltage, or in ohm related to primary or secondary side. So only based on short circuit impedance, we can determine voltage regulation, load distribution during parallel operation of transformers, and short circuit current. Impedance voltage of the corresponding transformer can be decreased by reducing the turns of LV winding and increasing the core window height. However, the lower the impedance voltage, higher will be the short circuit current during short circuit condition, which may lead to high stress on the winding insulation, as well as more copper must be added. This has become a challenging task to design for a closer compatibility between copper loss and iron loss. Analyzing transformer no load losses, and short circuit impedance, most dominating factors are to be seriously taken care of during selection of designing variables. Load loss would have been restricted by minimizing the number of winding turns, which implies that the core material as provided must be of higher magnetic flux density and of the largest practicable core cross-sectional area. So, no load loss, that is iron loss, has therefore to be increased with the increase of magnetic induction. In otherwise, by increasing the number of turns of LV winding, then no load loss would have been decreased. But at the same time, short circuit impedance has to be increased. As the no load loss is constant and continuous for a given applied voltage and being independent of load, so it is highly desirable to keep the no load loss always be minimum. So we are very much concerned about no load loss. Let's stop here. Further to be continued at later stage. Thank you for listening the video. Kindly do like, share, and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section. Thank you. Thank you for patient hearing.